Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Chris Mankovich with us today. Hey, Chris.
Hey, how you doing, Frank?
I am doing quite awesome on this April 18th of 2023 as we record this. And I'm here in Phoenix, and the weather is moving into our summer modes. So we'll get up into the 90s today, but it's a dry heat. It's a dry heat. And Chris, where are you at?
I'm in Los Angeles, where it's nice and sunny.
Very nice.
Still a little bit cold to call it summer. It's like a 65 or so.
Yeah, you get that big Pacific Ocean.
That's right.
Going there. Very cool. Very cool. That's an awesome kitchen. Is that real or is that an image?
It's a real kitchen.
Real kitchen. Very cool.
Yeah.
Nice.
That's where I start my mornings. Yeah, always a little bit of cereal, but the real essential part of breakfast over here is espresso, always.
Espresso. Yes, I have one of those, and we will be
very good
to go through. It's awesome. Very cool. And Chris, what do you like to do for research?
For research, I like to study giant planets, especially the gas giants in our solar system.
Nice.
So I've done a lot of work on Saturn and Jupiter. And I especially like to study these planets by studying the way that they oscillate, kind of like stars. They pulsate, and you can learn about their structure if you study those frequencies at which they pulsate. And that's most of what I spend my time doing, mostly using numerical models.
Very cool. And that is going to bring us to this very awesome Planetary Science Journal article. It's open access, people, so you can go get a copy for free. It's the open access era. Get one. Saturn's seismic rotation revisited. And Chris, take us away.
All right. So you can tell from the title already that this paper is a sequel of sorts, as all good content is nowadays. So this is a paper where we're trying to study Saturn's internal structure, and in particular the way that it's rotating in its interior by using Saturn seismology. And Saturn seismology is a little bit different from many types of normal mode seismology you might see applied to different astrophysical objects. It's very similar to astroseismology and global helioseismology in that we're studying this object using normal modes.
Okay.
But the way that we sample these normal modes for Saturn is pretty different, because they're not just directly observed in, say, brightness fluctuations over time.
Right.
Are actually only observable because of the fact that they're resonating inside Saturn's rings.
Ooh, nice. Okay.
So that's sort of the observational backbone of this paper, is observations of waves in Saturn's rings that were made using the Cassini spacecraft.
Okay.
And by measuring the locations of those waves, we're detecting frequencies of resonances with Saturn normal modes. And so that lets us measure normal mode frequencies coming from Saturn's interior. And so we have this whole spectrum of Saturn normal modes.
So there's a coupling between the interior and the rings.
Yeah, and it's just a gravitational coupling. So Saturn, the planet, is oscillating with these sort of planetary scale oscillations. There's a gravity fluctuation over time associated with those modes. And so each one can actually give you a resonance inside the rings. And many of these, dozens of these, are observed in Saturn's C ring, where it turns out that the optical depth is kind of this magic intermediate Goldilocks zone, where if you're staring at a bright star through the rings as the spacecraft tracks, you're scanning through these waves.
Very cool. Very cool. Nice.
It's a really cool thing that I certainly did not figure out. It's a pretty old idea that goes back to Voyager days, when radio occultations were showing some peculiar wave-like patterns. It turns out a lot of those are expected in the rings because of resonances with satellites. Just moons can have a similar effect, but many of these waves were in a location where there just wasn't a satellite resonance. And so there was this big question mark, which is, could we actually be seeing oscillations inside the planet itself? And there was some theory work when this was kind of a tentative idea by people like Mark Marley and Carolyn Porco, who were thinking about this problem. And then we had to wait decades for Cassini to go visit Saturn and orbit for long enough to confirm and find many, many more instances of this coupling between planetary oscillations and resonances in the rings. And so their ideas turned out to be 100% right. And we've learned a lot in recent years thanks to Cassini showing us so many of these. So if we want to get a kind of like a bird's eye view of what all these observations look like, maybe we can skip down to figure 12, which sort of gives a summary of the whole situation.
All right, here we go. Boom and boom. Resonance locations. There we go.
All right. So we're looking at a plot that is a function of just location in the rings. So I mentioned Saturn's C ring, which is just a part. It's not the brightest part of Saturn's rings. It's a little bit dimmer. It's a little bit interior to the very bright A and B rings that we all kind of know and love when we think of a picture of Saturn.
Yes. Okay.
So this is sort of 75 to 90,000 kilometers from Saturn's center. For reference, the total radius of Saturn is something like 60 in these units. So that gives you a little bit of a sense of scale here. And what we're looking at as a function of location in the rings is this number m, which is just the quantum number m. That is, it's an azimuthal quantum number that describes sort of a degree of angular symmetry as a function of azimuth. So sort of, yeah, exactly, L and M and LM. So you might recognize these from quantum mechanics. Or they pop up in sort of just dynamic astrophysical dynamics pretty often. So they're sort of symmetries. So when I talk about a resonance in the rings causing a wave in the rings, these waves are spiral density waves typically. Okay. Some of them are actually bending waves, which are similar spiral waves, but instead of epicyclic oscillations in orbit, they're vertical oscillations into and out of the ring plane. Okay. Cool. Small vertical oscillations. And so here we're seeing both of those classes of waves represented. All of these circle modes that you see on the plot are those spiral density waves. Okay. And spiral density waves might be familiar from spiral structure of galaxies and lots of astrophysical problems. Those diamonds are the other class. Those are the vertical waves. Okay, I'm with you. And the actual m number is just basically the degree of symmetry of those waves. So an m equals 2 wave at the bottom would be a 2-armed spiral, and an m equals 14 wave all the way at the top, that would be a 14-armed spiral. Okay. And these in Saturn's rings, the waves are really wound extremely tight. So it's really difficult to just measure the m value out of the gate. But if you are careful and you have a lot of data from Cassini, then you can sort of count these m values basically by tracking how quickly a crest will move over time. Okay, I'm with you. Good. So what we're seeing here is a bunch of data and a bunch of predictions from a model. And so the data are these big open symbols that we see. There's something like of order 30 on this plot. Yeah, so lots of the spiral density waves have been observed, and a smaller number of those vertical waves have been observed. And the smaller colorful symbols that cover the diagram are the answers for when we do a calculation from one of our numerical structure models for Saturn. Okay, cool. And yeah, there's some interesting stuff. In some places, it really agrees quite well. In other places, there's clearly more going on with the spectrum. There's two big classes of modes that turn out to be really important for understanding the spectrum that's seen for Saturn. Most of the resonances that are shown on this plot are just F modes, which are the fundamental modes. Okay. So in the analogy of a wave on a string, a fundamental mode is just like playing the open string, and it's the mode where you have just no nodes as a function of position along that string. It's just kind of the whole thing moving coherently. Yep. And stars and planets have the same class of modes, basically. The whole sphere moving. Yep. Yeah, like the whole sphere moving. And so you can have F modes for a variety of different angular structures. That's why we have so many things on this diagram. But it turns out that the spectrum also shows another flavor of modes that wasn't entirely expected for Saturn. And those are G modes. Yeah. So those might be familiar to people who study oscillations in stars. G modes are also a topic of a lot of discussion in helioseismology, although it's still not clear whether there are any G modes in the sun. So white dwarfs have G modes. And white dwarfs, of course. Yeah, G modes are huge for white dwarfs. So it's interesting that these are seen at all for Saturn because for Saturn, a very naive expectation for Saturn's interior is that it should be basically fully convective. Okay. Because it turns out that the interiors of these planets are really super opaque, and convection is kind of the most obvious way to explain their intrinsic flux. the fact that any G modes exist in Saturn means that at least part of the interior for Saturn has to be non-convective, because if you're convective, you can't sustain G modes. G modes are all about that buoyancy stabilizing the motion of fluids. So it requires a part to be stable against convection. And that was the biggest single surprise that came out of Cassini ring seismology in recent years.
That is very interesting.
And people like my co-author Jim Fuller were the first to recognize this in the spectrum, which had these surprises. To highlight the main kind of surprise in the observed spectrum, you can look at M equals 2 and 3, the lowest azimuthal order detections that are made for Saturn. Clearly, the spectrum does something different than it does elsewhere in this diagram, because here you have multiple observed waves with M equals 2 that are sort of split in frequency. At M equals 3, there's this even more peculiar phenomenon where there's actually 3 distinct detections there that are very closely spaced in frequency.
Yes.
Where models typically would only have a single mode there. And so we think at M equals 2 and 3, all of this sort of multiplicity of modes, which can't be explained by just rotational splitting, by the way.
Okay.
We think the reason for that is because there's this sort of additional spectrum of G modes that is really complicating the spectrum for Saturn.
Huh. Okay.
That's one of the things that we want to try to understand when we apply Saturn models to understand this seismic data set.
Yeah, interesting point there. Cool.
What this paper is mostly concerned with is actually the remainder of these modes. So all the modes that are farther up on this diagram, where G modes are not playing much of a strong role at all. These are basically pure F modes, and their frequencies turn out to be really strongly sensitive to Saturn's rotation. And that's part of the reason why this plot is showing a comparison between two different models. There's a rigid rotation model, which is these small open gray symbols. And then there's a model with quote unquote deep winds, which is addressing some differential rotation in Saturn's interior. And those will be the smaller, colorful blue and red points. Yes. And so, yeah, if you look very closely, like sort of where your cursor was pointing, at the highest M values, you can actually, on this diagram, you can see a significant separation between the rigid model and a deep wind model.
Yeah.
And that is the main crux of this paper, is trying to actually do a full-on inference using all of these observations and running many structure models to try to decide what is the optimum solution for Saturn's rotation. Okay. And that's both sort of the bulk rotation of the object in general, but also the degree of differential rotation.
Yeah.
Which it turns out, finally, we have enough data and we can run an accurate enough model that we can really pick out the signal of that differential rotation, which is the main point of this paper.
Nice. Very cool. Very cool.
And I think there's another plot that we can go to, maybe. I can't recall the number of the figure, but it would be toward the top. It's one that we'll say something like rigid model, one of the first few. So maybe it's figure 2.
Figure 2.
Yeah. So figure 2 is a good place to start. So on the left is where this is for a single Saturn structure model. Okay. It's for a rigidly rotating Saturn model.
Okay.
So it's important to note that we don't, even if you want to just build a rigid rotation model, it is not immediately clear what rotation rate Saturn is rotating at. It's actually sort of a big unknown.
Yes.
Saturn is a rapid rotator. It rotates at something like 40% of its Keplerian velocity, rotation velocity. That means that rotation is a major player when you're worried about any kind of force balance in this planet. It means that the Coriolis force is massive. And when you're trying to solve for the oscillations, that's really a big deal, because it changes sort of the way that all the modes behave, and it changes all of their frequencies. So that's an important thing to know. So what this plot is doing is it is picking an optimal rotation rate for a rigidly rotating Saturn model and then seeing how we do with its mode frequencies.
Okay.
So it is fit to the mode frequencies as best it can for a rigid model. And it's also fit to the gravity field, which is another important observational anchor for these structure models.
Okay.
So part and parcel with being rapidly rotating is the fact that your gravity field is no longer a point source gravity field. It's no longer spherical if rotation is significant. And so rotation introduces some oblateness to the planet. Saturn is actually rotating fast enough. It's visibly oblate when you look at a picture of it.
J2, etc.
Yeah, that's right. And that endows the gravity field with all of these non-spherical components. And so those can actually be measured directly by spacecraft. So in addition to the seismology, that is the single biggest constraint or set of constraints that we have on the interior density distribution of these planets. So that's another huge thing that you have to fit when you worry about all of this.
Okay.
So what this plot is showing is that the best rigid rotating model that we can make is not perfect. It's not even very good at all. So what we're seeing now on the x-axis is just basically a frequency residual.
Right.
For all of these frequencies, you can express them as a pattern speed. That's just a frequency of the mode, essentially. And what we're doing is we're plotting the residuals for this model, the modeled frequency minus the observed frequency, for this large set of observed frequencies.
I'm with you.
And these all have different values of m, and they all have different values of L minus m, which are just the indices that are describing the geometric structure of each mode. And on average, of course, they fit because the model was fit to these data, but systematically there are issues. And in particular, I'll draw your attention to, say, the black points, which are the L minus m equals 0 points.
Okay.
These are basically modes on the planet that have nodes as a function of azimuth, but they have no nodes as a function of latitude. So if you're picturing the spherical harmonic, it's one of the spherical harmonics that looks like a beach ball. It's just patterns of alternating positive and negative density or gravity perturbation as you go around this way. But if you go from pole to pole, there's no nodes.
Got it.
So many of those are observed, as you can see. And there is this systematic issue where clearly this model is biased. And as you go to the higher m values, you're finding that the model is more and more under predicting their frequencies.
Yeah.
And this is not a plot that we were always able to make. So in sort of the version 1 of this paper that I wrote when I was a grad student, that's a 2019 paper that sort of tried to look at this using rigid models.
Okay.
It was still using an approximate method for calculating the numerical mode frequencies for a given structure model.
Okay.
And an important advance of this paper is that we've gone to an improved method for calculating the mode frequencies for a model. And that's entirely thanks to the input of my co-author, Janos Dewberry, who's a postdoc at CETA in Toronto now, and developed a method for calculating the mode frequencies from a structure model with a non-perturbative treatment of rotation.
Cool. Okay.
So if you know a little bit about calculating mode frequencies for things like stars, then you know that rotation in some cases can be important, but it's typically slow enough that it can be treated as a small perturbation on top of the background problem of just solving for a mode in a spherical object. So it's treated as a little bit of a perturbation that can be calculated after the fact, sort of akin, again, to an example in quantum mechanics, where we've all heard of perturbation theory in quantum mechanics.
Right.
If your potential changes a little bit, you can build the full solutions out of the simpler solutions to the simpler problem that you started with.
Yes. But when the rotation is large.
But when the rotation is large, that is not such a small perturbation.
Right.
And first and even second order perturbation theories, which are, by the way, complicated enough as it is, they still might not be adequate. So for instance, for Saturn, if it's rotating at 30 to 40% of its breakup, that's sort of the critical spin parameter, is that fraction. A second order perturbation theory is only accurate to something like 5%. And here for reference, the frequency residuals we're looking at on the x-axis are 1 to 3 degrees per day. And the total pattern speed of each of these, the absolute scale of those, is like 2,000 degrees per day.
Oh, wow. Okay.
So we're looking at something like a part in 1,000, which is a lot smaller than 5%, you'll notice.
Yes, it is.
So for instance, even a second order perturbation theory is not going to cut it for this problem anymore.
Okay.
So anyway, what we have now is a non-perturbative calculation for the rotation. It's actually a significantly more sophisticated model that is directly accounting for rotation. So it has those effects incorporated accurately. And this is the first time that we've been able to run a model and look at these sectoral modes that have this sort of diagonal situation on this plot and say, that is a smoking gun that says that Saturn needs differential rotation.
Okay. Yes. Okay.
And that's something that we've already suspected just from gravity science. So it's been an interesting, say, 5 or 8 years, because Juno has been in orbit around Jupiter. Cassini was in orbit around Saturn for a long time. And one of kind of the blockbuster awesome achievements that each of those missions has done at those planets is to measure the gravity field so precisely that we can finally see the difference between a rigidly rotating planet and a differentially rotating planet. And so both of those missions have showed that those winds with their sort of conspicuous zonal wind patterns on the surface, where you have alternating eastward and westward patterns on the surface in the weather layer where you can see the clouds, it turns out that pattern does penetrate to significant depth in both planets.
Cool. Okay.
And so a major motivation of this was, okay, well, for Saturn, we also have this big set of seismology. Can we see those frequencies confirm what we think based on the gravity science? Do the zonal wind patterns on Saturn's surface actually extend to a significant fraction into the planet? And the answer is that they do.
Yes. Very cool.
So if you want to go to maybe a figure where we see what things probably actually do look like, then I think we can go to, was it figure 10? Or maybe it's somewhere in, why don't you just go ahead and scroll and we'll see it.
Figure 11, figure 10.
Let's go up a little bit more, because then we can see a similar plot. Yeah, so this is a plot that is now our notion of the most successful.
Oh, okay. Yeah, these two are similar to what we just looked at.
Yeah.
Rigid rotator.
Yeah, these two are exactly similar to that, but now for a model that is incorporating the fact that the rotation doesn't have to be rigid inside Saturn. There can be some differential rotation.
Yes.
And the picture at the left is the model that we're using to model Saturn's rotation as a function of depth. So this is a figure where you'll see that most of the planet is actually not rotating rigidly. So the color map here is just showing you the fraction of the total spin, the differential contribution to the spin as a fraction of the background spin.
Yes.
So you'll see that most of the planet is rotating rigidly, and we think that's for good reason. These are planets that when you get to depth, they're basically pressure ionized. Most of the interior is dominated by metallic hydrogen, which is very electrically conductive, and so it tends to resist any differential rotation. So it tends to rotate rigidly, because differential rotation would generate Lorentz forces that tend to subdue that differential rotation.
Okay.
So no shear at depth. And the key thing that we want to estimate is the depth to which the zonal wind pattern, which is the sort of alternating prograde and retrograde differential rotation that you're seeing in the red to blue colors. We want to know how deep that actually extends before it decays to this rigidly rotating background.
Yes.
And when we do this full problem, we fit the gravity field with all of these coefficients that are measured. We fit the seismology with all these frequencies that are measured.
Good.
This is the best it's kind of the best model that we can find when we do that. So this is a model where the deep interior is rotating at just shy of 635 minutes. So that's like 10.5 hours.
Okay.
And the wind decay depth is something like 13% of the planet's total radius, which is really spot on when you compare it with the estimates just from gravity science.
And that's this D over REQ.
Yeah, that D parameter is the wind decay depth.
I'm with you.
And you can see it helps us a lot with the mode frequencies, which we're seeing in the central panel here. Those are a lot closer to 0. They're certainly not perfect, but we think that this model does significantly better than a rigidly rotating model for sure. So I think we can rule out a model without deeply penetrating zonal winds for Saturn, which is great.
Yep.
I think the biggest piece of work to do here is to worry more about these low degree modes. So you can see at the lower values of M, which is incidentally where I showed you on the first plot that we talked about. G modes have more of a role, and you need to worry about things going on in the deeper interior where you might have stable stratification. And the degree of stable stratification affects the buoyancy frequency, which really affects the frequencies of all G modes. And so you have to worry about the particulars of the composition profile that you have in Saturn. That's right. So I think there's lots to be done there to improve clearly these outstanding residuals of several up to almost 6 degrees per day for some of these n equals 2, 3, 4, 5 modes.
Nice. Okay.
So that's the next target.
Cool.
So we don't just do this for a single model. We do this for a big ensemble of models and use Bayesian inference to estimate the parameters that go into this model. And this is a plot that summarizes sort of what the whole family of solutions looks like.
Nice. Okay.
Where the darker blue central cluster is our main sample of models that are fitting several of the modes and several of the gravity coefficients for differentially rotating Saturn structure models. And we're running many thousands of these on the fly and fitting them to those data sets using MCMC. And this is a plot that is just showing the distribution that you get in the space of the wind decay depth versus that deep fixed spin period for the planet.
Yes. Okay.
And our best model is there in the center with the special marker. That's the one that we were just looking at. But of course, there is a variance allowed for both of these parameters because it's a model with several parameters, and there are degeneracies that affect all the mode frequencies and all the gravity coefficients.
How about these other two with plus signs that are not in the middle?
This is trying to emphasize the additional value that the seismology has. So for instance, if you look at the plus signs or the distributions of models that they each belong to, so lighter greenish blue color and then the light green color, those are two distributions that are progressively less informed by the ring seismology.
Got it. Okay.
So we think the blue one represents the most realistic error bar for all the seismology. The light teal greenish blue distribution, that's the best model, and the distribution is quite large. It's covering a lot of the diagram. That's using artificially inflated error bars for the seismology. Okay. And then this light green distribution that we have in the background, where the best model happens to be all the way out there on the right, that's a model that is neglecting the seismology entirely, and it's fit just to the gravity field. And so I think that's the key takeaway from this, is that without the added benefit of that ring seismology, the deep spin period for Saturn can really be all over the map. Indeed. It turns out that the zonal wind depth is still somewhat constrained by just the gravity field because the gravity field really does pick up that influence of the deep zonal winds. But as far as nailing down the deep spin period, you really have a tough time without ring seismology.
At least getting some precision to it. Very good. Very cool. Very cool.
Yeah.
And what is this Mankovich 2019? How does that point relate?
So that would be the number and the error bars for our best guess for the deep spin period based on those earlier simple models. Right. So those are both simpler structure models, but the main limitation of them was using that perturbation theory to estimate the effect that rotation has on the modes. And so that was the answer that we get. And it's interesting to see that with newer models, more physically realistic interior models, but more importantly, a non-perturbative treatment for how rotation is affecting all of those mode frequencies. We get an answer that's consistent with those earlier models, but more accurate, thanks to the more accurate theory.
A little shift to the...
Yeah, a bit of a systematic shift.
Period, right. Right.
So we think, yeah, so now our best guess for the deep spin is a little bit slower than it was a few years ago. But now unlikely to change significantly from now on, given that the observational data set has grown to be so extensive over the intervening years. For reference, Mankovich 2019 was a paper that was based on more like a handful of modes that were actually known at the time. Okay. So even though Cassini, the mission ended in 2017 when Cassini, the spacecraft, dove into the planet Saturn and was destroyed, a lot of the data has really come since then. So it goes to show that missions need a lot of support for analyzing data that's collected for many years after end of mission. And so in the intervening years is when talented people like Matt Hedman and Phil Nicholson and Dick French and colleagues have poured over this data set of, like I described earlier, stellar occultations from one or more of the instruments on Saturn, and have pulled out increasingly weak signals in those stellar occultations that show wave patterns. Okay. With the right kind of analysis, at the simplest level, which is the level that I understand it, it's wavelet analysis of wave signals in the stellar occultations. By refining their methods over time, they're really pulling out more and more data out of this this fixed data set that is no longer growing. But the list of detections that they've made from that data set is still growing. And now there are something like 35 modes we can compare to.
Very nice. Good shout out. Good shout out. Very cool. Very cool.
So
there's also two hefty appendices. I will encourage people to take a look at those if they want. Got some more details in there, or if you want to cover something in there, or
definitely. So one of those appendices is pretty important because it describes the way that we estimate the effect that the differential rotation has on the gravity field. So I mentioned that the gravity field definitely gives away the fact these planets are differentially rotating, but calculating the effect that the differential rotation has on the gravity field in a model is not always straightforward. And there's some different methods used to do that. And this is another really nice piece of work that my co-author, Janos Dewberry, put into this paper. And this is a place you can go read about the exact method that's used to do that.
Very cool. I appreciate this level of detail for Science 101 verification. Yes, very good.
Absolutely. And there's another appendix that just shows, I mentioned those low M modes are clearly the most problematic for this model, and they show that there's more theoretical work to be done. So this is just a section that is addressing the question of whether fitting those modes with a model that clearly doesn't do a perfect job is biasing the results that we get for the rotation at all.
Yeah, so if you take them out.
Yeah, so the answer is, if you take them out, does it change your answer? And the answer to that is nope, not really.
Not really.
So here you have for the optimal model, you have a slightly faster deep spin and a slightly deeper penetrating zonal wind, but it's actually well within the distribution in the original model. So we find that they don't have a really important systematic effect on the answer.
Right.
But I encourage you to go look at all the details in the paper, of course.
Very cool. I have. You should too, people. Very cool. Very cool. Chris, I want to thank you so much for walking us through this very awesome article on Saturn's rotation. Very cool.
Of course. Yeah, I really appreciate the opportunity. Thanks a lot.
Yeah. And you mentioned it a couple of times, at least two different ways, and I'll just push on that a little bit. So where do you think we go over the next couple of years on this topic? Will there be enough teasing out of the data instead of having 35 modes? Are we going to get 100 modes? What's sort of an upper bound there? Is there additional theoretical work that could be done on including G modes? Just sort of where do we go with this topic over the next 2 to 5 years?
Yeah, that is a very important question to me and hopefully to everyone. I think first, observationally,
yes,
100 modes is not very likely, but several more certainly within the realm of possibility. I wouldn't be entirely surprised if they found another dozen or 24 with the existing data.
Okay.
My personal hope is that if there are any more detections made with the existing Cassini data, there are new detections at low M, which the spectrum that we showed has lots of predictions for low M, especially because as soon as you start considering G modes, there's really a whole sequence of G modes that might appear. And those would really be precious because more G modes would be indispensable anchors for understanding that the stable stratification and the deep interior. So does Saturn have a diffuse core? How diffuse is it? Could there be more than one composition gradient? There's definitely physical motivation for considering more than one stabilizing composition gradient in Saturn.
Yeah.
So a new detection at low M would be huge. I'm holding out for even one more detection at low M. That would be a big deal for this science.
Nice.
Two, future theoretical work that can be done right now and is being done right now.
Okay.
Is sort of on a similar question. Even with the existing data, the fit is not perfect. So we don't need more data to learn something new because we can't really declare victory until we can explain the frequencies of these different detections. And I think a huge part of that is what I already alluded to, which is the fact that physically, we think there probably is more than one stably stratified region in the planet. Yeah. And that's something that needs to be explored systematically and just hasn't been so far.
Okay. Okay. So
and then taking a step a little bit farther back, even forgetting about Saturn, where it's unlikely that we'll have another Cassini very soon. There are other objects inside the solar system that we really don't understand, especially in the outer solar system, where there are these planets, Uranus and Neptune, that have even more mysterious deep interiors and rotation states than Jupiter or Saturn. And it's likely that Uranus is going to be the target of the next serious large-scale exploration in the solar system. And
Uranus has rings, so you can do the same.
Yeah, so there's the possibility. Uranus has a ring system. Admittedly, it's not exactly Saturn's ring system.
Yeah,
which is nice and flat and uniform, but there are rings there, and there's certainly the possibility that one or more of them could be coupled to the interior the same way that Saturn's rings are coupled to its interior. And so one of the things that I'm really interested in exploring is whether we can expect Uranus normal modes to be resonating in its ring system, which would be huge because so little is understood about the interior of Uranus or Neptune.
I smell
it would be great to get a number or two just to try to work that out.
I smell a prediction it can be coming before it's measured.
Yeah, that's quite right. That's quite right.
Very cool. Very cool. Although post-diction is nice too, but prediction is even better.
Way better. Way
better. Very cool. Chris, I want to thank you so much for taking some time and walking us through your very lovely PSJ article. Very nice.
Thank you, Frank. And thanks to everyone for listening.
Sure. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.